Hello everyone. So today I want to go through stereoisomers, and the reason that I decided to make a video on this topic is because this was one of the things that I found really tough to grasp as when it was first introduced. And so you might know where this first image is from. It's actually straight from John's notes. So what I want to do is I kind of want to break this chart down in my own way, in the way that I understood it. And after that, I want to maybe do some practice problems and just go through kind of my approach to solving questions where you're trying to determine what kind of relationship there is between two molecules. Before we start, I do want to emphasize that practice is by far the best way to get a good grasp on this topic, and really any sort of topic in organic chemistry. And so, like, these charts will only be able to help you so much, right? But it's a great place to start. So that's kind of what I want to do. So when I first saw this, I actually had a pretty tough time breaking it down. So what I have here is another chart that I kind of made with the help of actually a TA from last year. And so I kind of want to go through this, and then hopefully this will help us understand this first chart, and then we'll go through some strategies, and we'll end it there. So let's get started. So in this chart, um, basically this chart can be used basically whenever we're comparing two molecules, right? So the first thing we want to check is the molecular formula of a molecule. And if we see that the molecular formula is not the same, we can already determine that they're not isomers, right? And if they are the same molecular formula, we have a bunch of other things to check. So the first thing that I would always check is if the two molecules are superimposable mirror images. Now this seems like really obvious, but this is actually a step that a lot of times like you might miss just kind of in the heat of the moment, and that always sucks because like you spend so much time trying to solve the question and it turns out it's just the same molecule, right? So always make sure to check this. This is very important. Okay, let's say that we don't have identical molecules. So then what we see is if the atoms are combined in the same order. And if they're not, we can determine right away that they're constitutional isomers. But if we see that they are combined in the same order, then we determine that they're stereoisomers. Now comes the tough part, is figuring out what kind of stereoisomer, right? And so what we want to first look at is if within the compound you can rotate a single bond so that you get the other molecule, and what you'll end up with is a conformational isomer. If this isn't possible, we look at if they are isomers due to restricted rotation. So this basically means when we have something like a molecule like this is a pi bond which cannot rotate, right? And so this would make it a diastereomer. And when we see that, we want to try to name it. And this is something that's covered in class, and we won't be covering in this video. But just really quick, you have your E and your Z alkenes, and then you also have your cis and trans for your cyclomolecules. Finally, if they aren't isomers due to restricted rotations, we want to check if they're exact mirror images. And so this is actually easier said than done. We'll go through some strategies to determine that. But this is the place where I feel like most people struggle. And so this is kind of the part where I want to focus this video on, as well as put an emphasis on um, the same molecules, because a lot of times we get stuck in trying to figure out this step, but really they just end up being the exact same molecule. So one thing I want to do is I want to cover the fact that there's a way that you can always get the right answer, right? And so this is something that was talked about in class. And so that way, obviously, is to assign priorities. And so we'll really quickly cover that because this is always a great way to do it. So basically, let's just go through this. All right. So we notice that chlorine gets our number one priority because it has the highest atomic number. And second up, it's going to be one of these carbons here, but we're not sure which one because carbon has, obviously the same atomic number as the other carbon. So what we do is we look at the next atoms that they're attached to. So we see they're attached to two hydrogens. So let's look at the next one. So another two hydrogens, exactly the same. But then we notice that this carbon is attached to a carbon and this one's attached to a hydrogen. Since carbon has a higher atomic number, we give this a 2. And then next we want to give this a 3 because that's another carbon. And then our final one is the hydrogen here. And once you've determined, here, let me erase some of these arrows. Once you've determined what your priority is, the next thing you want to do is you want to look at if your least prioritized atom in the molecule faces towards you. So towards you meaning it's a wedge, or if it faces away from you, so that means it's a dash. And so if it's facing away from you, so the dash, what we can do is we can very easily draw a little circle like this, because we see it goes from here, let me switch to the laser. It goes from 1, 2, 3, then 4. So we get a nice sort of uh, clockwise circle like that. And a good way to remember that clockwise is R is that when you're like drawing an R, I guess you go like clockwise right there. I don't know. That's a way I remember it. And then if it's the other way around, like this, it's kind of like the top of the S there. So you can remember R and S kind of like that. But always remember that if the least prioritized molecule is facing towards you, you have to reverse that, right? So, your mileage may vary with my strategy here with the R and the S, but that's just a way I remember it. Okay, so this is always a way to get the answer if you have the time, but a lot of the times on a test, you don't have that much time, right? Or a quiz or whatever it is. And so the best way to learn how to do those questions is just straight up practice. And so what we'll do next is we'll kind of go through some practice problems. And what I want you to do is pause the video and try these before I go through them. And I'll kind of explain my thought process. And what I want to relate my thought process to is this chart here. So in all our examples here, they will all have the same molecular formula. So we'll kind of skip that step, but we'll go from there. So pause the video, try these questions. Here's two, and then here are the other two, and then we'll go through them. All right. Okay, so I hope you've tried the questions. So we're going to go through these, and I'm going to kind of explain how I would do them if I was in a test scenario, or just in general how I would solve them in what I believe is the quickest way possible. So when I look at these molecules, the first thing I want to check always is, are they the same molecule? Like, can I somehow turn this molecule to give me this molecule, right? And so what I realized very quickly is that I can't do that. Like, if I flip the first one, if I do anything to this first one, it like I can't get this over here, right? And so what I will do is I will very quickly look at the fact that this is a wedge and this is a wedge and this is a wedge, but this is a dash. And so what that tells me is I don't really care if this is R or S, right? But I know that this bond and this bond are going to have the same assignment. So those could be R or S. I'm not going to determine that, but I know they're going to be the same. And then I look at this one, and I notice that they're not the same. They're different, right? And so a rule that we looked at was that if they're exact mirror images, if they're not exact mirror images, we have diastereomers here, right? So even if this is an R and this is an R, and let's say this is an S, well, this one then has to be an R. And since these groups are different, we can very quickly determine these are diastereomers. I'll just write D here. And so you might feel a little confused there. Maybe I went a little fast, but this is sort of my thought process here. And this will develop with practice. Practice is the most important thing. So the main thing that I looked at here was the fact that this bond and this bond are different, but this one and this one are the same, which screams diastereomer to me. Okay, let's look at the next one. So this is a tricky one actually, because when you first see this, it's sort of similar where like you have two that are the exact same on both the molecules, but then these two seem different, right? So you're like, oh, not all of them, not all the wedges switch to dashes, not all the dashes switch to wedges, so it must be diastereomers. But we look back and we look at what the number one thing to check is, and that is if they might be identical molecules. And you'll notice very quickly actually is that if you just turn this way like 90 degrees, you will get this exact molecule. And so it actually turns out that these are the same. Okay, let's go on. All right, same, just to not confuse you with S. Okay, so one thing I found very tricky was Fisher projections relating to stereoisomerism. So what I want to look at is this first molecule, and this one can seem quite tricky. And so again, I look at this and I'm like, oh look, these two are on the other side of this one, so they must be mirror images. But what you'll notice very quickly, if you check the first rule that I mentioned, is that if you take this molecule and just flip it around, you end up with this exact molecule. And so actually in this example we have the same once again. All right. And now the final one, so this final one's actually very similar to our last example. And so this one actually we go through, we're like, okay, first, Raja said always check if they're the same. So let's check. Oh, maybe I can flip it this way and I get the exact same molecule. And so what I mean by flip this way is that this bond sort of here in the middle stays constant and you kind of rotate it like a cylinder. And so what you may think is you end up with something that looks like this. But what we have to remember is that Fisher projections actually are technically wedges here. So these are wedges. And so when we flip it around, these bonds right here actually become dashes like this. And we know that these two would be enantiomers then, because we know that these are also wedges. That's how Fisher projections work, right? And so these can be very tricky. Like I'd say the Fisher projection questions were probably the ones that took me the longest to figure out. Oh, by the way, these are enantiomers. Enantiomers. A good way to always get Fisher projections, and I guess any question in this regard, is to assign RNS. I still will assign RNS just to make sure. I designed this question, so I was able to quickly figure it out. But in a testing scenario, if I was to allocate time, I would definitely allocate time to the Fisher projections because they can be pretty tricky. Sometimes drawing these wedges in can really help. And yeah, so those are just a couple examples. I highly, highly recommend you go through all the examples given in class, all the problem sets, but also try looking up problems online. It's very easy to find, problems on stereoisomerism because a lot of people do struggle with this. Also, check out my resource sheet where I have a lot of videos linked that are great. They have lots of practice problems. I only gave 4 here. Some of them have way, way more. So I highly recommend those. And what I really want to highlight is that this chart is a very good place to start, but the best way to kind of get this down in your mind is to do practice. So if you have any questions, please feel free to contact me and let me know if I can help. And I hope you enjoy the video. Thanks for watching.